Hello, in this section we're going to finish up Chapter 9 by talking about one additional theory. This is sort of the next level that you can take in terms of understanding bonding in molecules, and that's what we call molecular orbital theory. And this takes the same ideas that we use to figure out the orbitals in atoms and apply it to molecules, and finding the orbitals that exist not just on a single atom, but how they can spread out and be part of a whole molecule. Now, why do we need this extra theory? Well, there are a few things that we can't explain through valence bond theory and through VSEPR theory. VSEPR theory does accurately predict shapes of molecules, but there are a few things that we can't predict. One, for example, is that the molecule nitrogen is what we call diamagnetic, meaning that it's repelled slightly by magnetic fields. It's kind of hard to measure this since it's a gas, but if you liquefy nitrogen and you put it next to a magnet, it will be repelled by a magnet. On the other hand, if we look at oxygen, O2, it is paramagnetic, which has the opposite. It means that if we put liquid oxygen, or even gaseous oxygen, but it's easier to see with liquid oxygen, it will be slightly attracted by a magnet. So that's one example of a property that we don't, in valence bond theory, we don't really have a good explanation as to why this would be different. The only difference is that one has, O2 has a double bond, and N2 has a triple bond, but it's not clear why that would change the properties of being paramagnetic or diamagnetic, because paramagnetism is caused by unpaired electrons, and according to valence bond theory, everything is paired and is in a pi orbital. But there must be some explanation as to why we get unpaired electrons in O2. And molecular orbital theory does accurately explain this. One of the other things that molecular orbital theory can help to explain is the spectra of molecules. Meaning that just like in atoms, we can see transitions between different energy levels. We talked about this with the hydrogen atom in particular, but it applies to all other atoms. The same thing that if we put energy into a molecule, there are different orbitals, and we can see transitions from a higher energy state to a lower energy state, and those will emit light, or the other way around, that they can absorb light. And the spectra can't be explained with valence bond theory or just by the shapes of the molecules alone, but we also need to understand what are the different orbitals in terms of the molecule. So that's why this theory is necessary, and it really builds on the ideas of quantum mechanics that we talked about, just like the other theories we've talked about too, just like valence bond theory does as well. But here, if with valence bond theory, just like what's different here? In valence bond theory, we're thinking about everything in terms of atomic orbitals that then overlap to form bonds. So we're thinking about like hybrid orbitals on, say, a carbon atom or something like that, or let's keep it simple, hydrogen atoms, right? So we have our 1s orbitals. If we put them close together, they're going to overlap, and this overlap between the orbitals is what we call a bond. The difference with molecular orbital theory is that instead of thinking about our orbitals overlapping, instead we're thinking about combinations of orbitals, where the molecular orbitals, right, these are atomic orbitals overlapping, thinking about one single atom. In molecular orbital theory, we think about an orbital that spreads across the whole molecule instead. We'll look at these in a bit more detail in the next video, but if we combine two hydrogen atoms, we actually get an orbital. If these dots represent the nuclei, that actually spreads across both atoms. So it's not a 1s orbital on one hydrogen or the other, but it's this different thing that's combined. And we'll also see there's actually a different orbital that looks like this. We actually get two different orbitals. And again, they spread across the whole molecule. And this applies even to larger molecules than hydrogen, where you get orbitals that spread across the entire molecule. And so molecular orbitals are very good for explaining delocalized electrons as well. We don't have to sort of come up with resonance structures and all that is just sort of built into the theory that electrons will spread across the whole molecule, and that's sort of always the case. And your molecular orbitals will, in general, sort of spread out across the entire molecule. All right, so that's our little bit of an introduction to molecular orbital theory. We're not going to go too deep into this. We're just going to look at diatomic molecules, so molecules that only have 2 atoms, and we're just going to look at the first and second rows of the periodic table and limit ourselves to things that have the same atoms, so what we call homonuclear diatomic molecules, things like H2. We'll even look at some molecules that that don't actually exist or are very difficult to make. Anyway, so we'll get to that in the next video. In the next video, we'll look at hydrogen and helium as sort of our first look at this, where we only have one atomic orbital to worry about, which is an s orbital, and then we'll move on to the second row of the periodic table.